Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to Computer Architecture and Assembly Language class. So today we will focus entirely on instruction set architecture. In our first lecture, we introduced ISA as the critical interface between software and hardware. We discussed how it defined the set of instructions a CPU can execute and how it serves as the bridge between high-level languages and the physical machine. Now we will go much deeper. Let's begin. Okay, here is an outline of what we will cover in this lecture. We begin with instruction set design, looking at the fundamental decisions architects make when creating an ISA. Next, we discuss RISC design principles, which guide the design modern processors like MIPS and ARM. Then we introduce MIPS registers, the small, fast storage locations inside the processor that instructions use. After that, we cover instruction formats, which define how instructions are encoded as binary numbers. We then look at immediate operands, which follow instructions to use constant values directly. Next is bit manipulation, including logical operations like AND, OR, and shifting. We then discuss load and store instructions, which move data between memory and registers. Following that, we cover byte ordering, specifically big endian and little endian formats. And finally, we explore addressing modes, which determines how instructions specify the location of their operands. So this is our comprehensive list, and each topic builds on the previous one. Let's work through them step by step. Okay, just to recall from our first lecture, ISA is the interface between software and hardware. It defines the set of instructions that a processor can execute, including their format, what operations they perform, and how they access data. Think of it as the language that software uses to communicate with the hardware. Okay, this section will cover the principal type and categories of instruction sets. Instruction set design formats the foundation of computer architecture and plays a crucial role in determining the capabilities of a computer system. Let's explore it further. A well-designed ISA plays a critical role in determining a processor's efficiency, compatibility, and ease of programming. Here are the key principles shown on this slide. Okay, simplicity means keeping instructions easy to decode and execute. Orthogonality means instructions and operands can be used independently without restrictions. Regularity means similar operations follow consistent patterns. Uniform data type means data is handled consistently across instructions. Efficiency means instruction executes quickly and use hardware effectively. Code density means program should be compact in memory. Addressing mode define how instructions access data. Data flow determines how data moves between registers and memory. Load store architecture means only load and store instructions access memory, while other all operations work with registers. So reduced instruction set means having fewer simple instructions that execute in one cycle. Compatibility means new processor can run old software without modification. Scalability means the ISA can work across different implementations from small embedded devices to high performance servers. Privileged levels provide hardware support for operating system by separating user mode from kernel mode. Standardization ensures the ISA is well defined and consistent across different implementations. Openness means the ISA specifications are publicly available for others to implement. Optimization for common workload means the ISA is designed to handle frequently used operations efficiently. And error handling defines how processor detects and responds to illegal operations or hardware faults. All these principles work together to create processor architectures that are efficient, versatile, and user-friendly, supporting a wide range of applications. Okay, this slide reviews the two main type of instruction set designs which we introduced already in our very first introductory lecture as well. First is RISC, which stands for Reduced Instruction Set Computer. RISC architecture is designed to simplify the individual instructions given to the computer to accomplish tasks. Because each instruction is simple, a RISC program might require more total instructions to complete a task compared to CISCs. However, these simple instructions can execute very quickly. Second is CISC, which stands for Complex Instruction Set Computer. In a CISC architecture, single instructions can execute several low-level operations, such as load from memory, performing an arithmetic operation, and storing the result back to memory. CISC instructions are also capable of multi-step operations and complex addressing mode within a single instruction. As mentioned in our first lecture, these represent two different design philosophies. RISC focuses on simple, fast instructions, while CISC focuses on powerful multi-operation instructions. So both operations have strength and used in modern processors. Now let's dive into RISC design principles. RISC, which stands for Reduced Instruction Set Computer, is a design philosophy that emphasizes simplicity and efficiency. Instead of providing many complex instructions, RISC processors utilize a small number of optimized instructions to achieve improved performance and power efficiency. The idea is that simpler instructions can execute faster and consume less power, even if a program needs more of them to complete a task. This approach also makes the processor hardware simpler and easy to design. We will now discuss the characteristics and advantages of RISC design in more details in the coming slide. So RISC or reduced instruction set computer is a type of computer architecture known for its simplicity, efficiency, and performance. The core idea behind RISC is that a smaller, simpler set of instructions lead to a faster and more efficient processor. By keeping instructions simple, the hardware can execute them quickly and with less power consumption. Let's go to the key characteristics of RISC architecture shown on this slide. First, RISC architectures are designed with a minimal and regular instruction set. This simplicity makes it easier to design, implement, and optimize the processor. Each instruction typically performs a single, well-defined operation, so there is no complex instructions that does multiple things at once. Second is fixed length instructions. RISC instructions are of fixed length, usually 32 bits. So this uniformity simplifies the instructions fetch and decode stage in the processor. The hardware always knows exactly how long each instruction is, which leads to faster execution. Third is the load store architecture. RISC architectures follow a load store model. This means that only load and store instructions access memory directly. All other operations such as arithmetic and logic are performed on the data stored in registers. By minimizing memory access, performance improves because registers are much faster than memory. Fourth is a large number of registers. RISC architectures typically includes a large number of general purpose registers, often 32 or more. Having more registers reduces the need to access memory for immediate data storage. Data can stay in registers longer, which leads to faster execution. Interestingly, the concept of using registers for storage dates back thousands of years, but in its modern format, it is key RISC feature. Fifth is execution. RISC instructions are designed to execute in a single clock cycle. This results in predictable and fast instruction execution. Complex operations that could normally take multiple cycles are broken down into simpler atomic steps to maintain the single cycle execution model. Sixth is compiler-oriented design. RISC architectures are designed with the expectation that compilers will be used to generate code. They aim to make it easier for compilers to optimize code and use available registers effectively. The hardware simplicity shifts some complexity to the compiler. Seventh is hardware control unit. RISC processors used a hardwired control unit rather than microcode. This means the control logic is built directly into the hardware using logic gates. A hardwired control unit uses a simple decoding mechanism to select the appropriate instruction to execute, which is faster than looking up microcode routines. Eighth is fixed operand format. RISC uses fixed operands for specifying registers and immediate values. This consistency makes it easier for the processor to decode and execute instructions quickly because the operand locations are always known. These 8 characteristics together define the RISC design philosophy and explain why RISC processors can achieve high performance and power efficiency. Next, ninth is the pipelining. RISC architectures are well suited for pipelining, which allows multiple instructions to be in various stages for execution simultaneously. Because instructions are simple and uniform, they flow through the pipeline smoothly. This contributes to the high throughput and performance. 10th is energy efficiency. RISC architectures are known for their energy efficient design. The simpler hardware and reduced complexity means less power consumption. This makes them especially suitable for battery-powered devices like smartphones and tablets, as well as any application where power consumption is critical. 11th is reduced complexity for complex operations. So complex operations such as floating point arithmetic are implemented using sequence of simpler instructions rather than having complex instructions that do everything at once. This approach simplifies the design of the processor while still supporting advanced operations. 12th is low latency. RISC processors are designed to have low instruction execution latency, meaning each instruction completes quickly. This makes them suitable for real-time and high-performance computing applications where response time matters. 13. Scalability. RISC architecture are highly scalable, allowing for easy integration of multiple cores or processors on a single chip. This scalability is beneficial for parallel processing and multi-core systems, enabling performance to increase by adding more cores rather than making individual core more complex. 14 and last is open architectures. Some RISC architectures like RISC-V are open and royalty-free. This openness encourages innovation and customization because developers and companies can design their own processors without paying license fees. It also fosters collaboration and wider adoption across the industry. So these 14 characteristics together explain why RISC have become the dominant design philosophy in modern computing, from mobile devices to cloud servers. Now let's summarize the advantages of RISC architecture. Simplicity comes from having a small regular instruction set that is easy to implement. High performance results from instructions that executes quickly and pipeline that run efficiently. Reduced memory access is achieved through the load store architecture, where most operations work with registers instead of memory. Efficient use of registers means data stays in fast storage longer, reducing slow memory accesses. Compiler friendliness means the regular instruction set makes it easier for compilers to generate optimized code. Pipelining works smoothly because instructions are uniform and predictable. Energy efficiency comes from simpler hardware that consumes less power. Scalability allows multiple cores to be added easily for parallel processing. Reduced complexity for complex operations means even complicated tasks are broken into simple, fast steps. Open architectures like RISC-V encouraged innovations and lower costs. Predictable performance comes from single cycle execution and consistent instruction behavior. Reduced instruction latency means each instruction completes quickly, benefiting real-time applications. Low cost results from simpler hardware design and wider adoption. So these advantages explain why RISC has become the dominant choice for modern processors across all computing domains. Now we move from general RISC principles to specific example, the MIPS architecture. MIPS is microprocessor without interlocked pipeline stages. It is a RISC architecture developed in the 1980s by Stanford University and later commercialized by MIPS Computer Systems. MIPS is a classic RISC implementation that perfectly illustrates the concepts we have been discussing. This diagram shows the overall organization of a MIPS processor. At the center is the CPU, which contains several key components. The CPU has a set of general purpose registers numbered from $0 to $31. These are the fast storage locations that all arithmetic instructions use. The arithmetic unit performs integer operations like addition and subtraction. There is also a separate multiply and divide unit with two special registers, low and high. Multiplications and division results are stored here because they may be longer than normal register width. The diagram also shows coprocessor 1, which is the floating point unit or FPU. It has its own set of 32 floating point registers and an arithmetic unit for handling floating point calculations. Finally, coprocessor 0 handles traps, exceptions, and memory management. It contains special registers like bad virtual address, which stores the address that caused an error, status, which controls processor operation, cause, which indicates why an exception occurred, and EPC, exception program counter, which holds the address of the instruction that caused the exception. So this organization reflects the RISC philosophy: separate units for different tasks, many registers, and a clean division between integer, floating point, and system operations. This slide shows how a program is organized in memory when it executes. At the very top, starting from address 0x7 FFFFFF, this is hexadecimal number, and growing downward, we have the stack segment. The stack is used for temporary data like function parameters, return addresses, and local variables. It grows and shrinks as functions are called and returned. Below the stack is the dynamic area, also called the heap. This is where dynamically allocated memory lives, such as when a program uses malloc in C or new in C++. The heap grows upward towards the stack. Next is the static area. This holds global and static variables that exist for the entire lifetime of the program. These variables have fixed memory locations. Below that is the text segment. Starting address 0x00400000, that is again hexadecimal number in MIPS. The text segment contains the actual machine instructions of the program. This is where your compiled code lives. At the very bottom is the reserved area, which is typically off limits to use programs and used by the operating systems. Notice that the stack grows downward from high memory addresses while the dynamic area grows upward from lower addresses. This arrangement allows both areas to share the available memory space efficiently. If they meet any point, the program runs out of memory. Now let's focus on MIPS registers. In the MIPS architecture, registers are the fast temporary storage locations inside the CPU. They play a vital role in storing data and operands, facilitating computations and managing control flow within the processor. Unlike memory, which is large but slow, registers are small but extremely fast. MIPS provide 32 general purpose registers, each 32 bits wide. Because MIPS follows the load store architecture we discussed earlier, all arithmetic and logic operations must use registers. Memory is accessed only through dedicated load and store instructions. We will now explore the types, purpose, and organization of MIPS registers. Let's proceed for that. This slide shows the 32 general purpose registers in MIPS, each with a specific name, number, and usage convention. Register 0 is $0. It always contains the constant value 0. This is useful for comparisons and initializing values. Register 2 and 3 are $V0 and $V1. These are used for values returned by functions and for expression evaluation. Registers 4 through 7 are $A0 through $A3. These holds arguments passed to functions. Registers 8 through 15 are $T0 through $T7. These are temporary registers. If you call a function, the called function is free to override these. So the caller must save them if needed later. Registers 16 through 23 are $0 through $7. These are saved registers. If you use these in a function, you must save their original values and restore them before returning. The caller expects them to be unchanged. Registers 24 and 25 are $T8 and $T9. These are more temporary registers with the same convention as $T0 through $T7. Register 28 is $GP, the global pointer. It points to the middle of a 64K block of memory holding global variables. Register 29 is $SP, the stack pointer. It points to the top of the stack, which grows downward. Register 30 is $FP, the frame pointer. It points to the current stack frame and is useful for debugging and variable length arrays. Register 31 is $RA, the return address. When a function is called, the return address is stored here so the program knows where to continue after the function completes. So these conventions are not enforced by the hardware but are followed by software and compilers to ensure different functions can work together correctly. This slide explains why registers are so important in computer architecture. Registers are small, high-speed storage locations within the CPU used for various purposes in instruction execution. First, data storage. Registers hold temporary data that the processor is currently working on. Second is address storage. Registers can hold memory addresses for load and store operations. Third is operand access. Most instructions get their operands directly from registers because register access is much faster than memory access. Fourth is control and status. Special registers hold information about the processor state, such as condition codes or exception information. Fifth is function arguments. Register pass parameters to functions, avoid slower memory access. Sixth is context switching. When the operating system switches between programs, register values are saved and restored. Seventh is reducing memory access. By keeping frequently used data in the registers, we avoid slow memory accesses, which improves performance. Eighth is parallelism and pipelining. Having many registers allowing multiple instructions to work on different data simultaneously in the pipeline. Ninth is scratch space. Registers provide temporary storage for intermediate results during complex calculations. 10th, architectural and general purpose registers. These are the registers defined in the ISA that programmers and compilers can use directly. So in summary, registers are the fastest memory in the system and are essential for achieving high performance. This slide explains how registers and memory work together in MIPS. First, a key rule in MIPS, arithmetic instructions operands must be in registers. You cannot add two values directly from memory. You must first load them into registers, perform the operation, and then optionally store the result back to memory. MIPS has 32 registers available for this purpose. Compilers work hard to associate frequently used variables with these registers to keep data close to the processor. But this raises an important question. What about programs with lots of variables like large arrays or complex data structures? 32 registers may not be enough to hold everything at once. The answer is that we use memory for the rest. The program keeps most data in memory and used load and store instructions to transfer data between memory and registers as needed. When there are not enough registers for all active variables, the compiler spills some registers to memory. This means temporarily saving register values to memory and loading them back later when needed. This is why the load store architecture we discussed earlier is so important. It makes the register usage explicit and predictable, which helps compilers manage this spilling and filling efficiently. This slide shows the complete organization of all 32 MIPS registers with their names, numbers, and usage conventions. Let me go through them systematically. Register 0 is $0. It always contains the constant value 0. Register 1 is $add. Reserves for the assembler. The assembler used this for translating pseudo instructions. Register 2 and 3 are $V0 and $V1. They hold expression evaluation results and function return values. Registers 4 through 7 are $A0 through $A3. These are the four argument registers for passing parameters to functions. Registers 8 through 15 are $T0 through $T7. These are temporary registers not preserved across functions calls. If you need the values after a call, you must save it. Registers 16 through 23 are $S0 through $S7. These are saved temporary registers preserved across function calls. If you use them, you must restore the original values before returning. Registers 24 and 25 are $T8 and $T9. More temporary registers with the same conventions are through $T0 through $T7. Registers 26 and 27 are reserved for the operating system kernel. User programs should not use them. Register 28 is $GP, the global pointer. It points to a static area of the accessing global variables. Register 29 is $SP, the stack pointer. It points to the top of the stack. $30 is $FP, the frame pointer. It points to the current stack frame. Register $31 is $RA, the return address. It holds the address to return to after a function call. So these conventions ensure that efficient functions and compilers can work through predictably. Now this slide reinforces the relationship between registers and memory in MIPS. Let's start with the key point. Arithmetic instructions operand must be in registers. In MIPS, you cannot directly add two values stored in memory. You must first load them into registers, perform the addition, and then optionally store the result back. This is why MIPS has 32 registers available for this purpose. Compilers work to associate frequently used variables with these registers. Keeping data in the registers rather than memory speeds up execution significantly because registers are much faster. But what about programs with lots of variables with large arrays or complex data structures? As we discussed earlier, 32 registers may not be enough to hold everything simultaneously. In this case, we use memory for the bulk of the data. Load and store instructions transfer data between memory and registers as needed. When there are not enough registers for all active variables, the compiler spills registers to memory, temporarily saving registered values to memory and loading them back later. This design is why MIPS is called a load store architecture. Only and store instructions access memory. All other operations work exclusively with registers. The diagram at the bottom shows the bigger picture. The processor contains registers and control logic. It connects to memory and input-output devices. The load store model creates a clean separation where the processor works on data in registers and dedicated instructions move data between registers and the outside world. Here we explain how memory is organized in MIPS. Memory is viewed as a large single dimension array with each location accessible by an address. A memory address is simply an index into the array. MIPS uses byte addressing, which means each address points to a single byte of memory. The table on the right show that each address points to a single byte of memory and address 0 points to 8 bit of data, address 1 points to the next 8 bits and so on. The smallest unit you can load or store is 1 byte. However, most data items we work with are larger than a single byte. Integers, for example, typically use 4 bytes. In MIPS, a word is defined as 32 bits, which equals 4 bytes. The diagram on the right illustrates this, while memory is byte addressable, a 32-bit word occupies 4 consecutive bytes. So, word at address 0 occupies bytes 0, 1, 2, and 3. The next word at address 4 occupies byte 4, 5, 6, and 7. This is important because when we load a word from memory, the processor fetches 4 bytes starting from the specified address. The address must typically be aligned to a multiple of 4 for efficient access, meaning the address should be divisible by 4. So in summary, memory is byte addressable, but we often work with 4-byte words. This distinction matters when accessing data and when we calculate the addresses. Instruction formats dictate how instructions are structured, encoded, and implemented by the processor. And it also shows that how it is interpreted by the processor. Each instruction is a 32-bit pattern and the format determines what each group of bits represent. We will explore different formats, encoding techniques and the field structure of instructions. Understanding instruction format is crucial for effective programming and hardware design. It helps you understand how the processor decodes and executes the instructions you write. So let's continue on this. MIPS instructions are all 32 bits long and comes in 3 formats. First is R-type, used for register to register operation. It has fields for 2 source registers, 1 destination register and a function code. Second is I-type, used for instructions with an immediate constant. It has 2 register fields and a 16-bit immediate value. Third is J-type, used for jump instructions. It has a 26-bit address field for targeting jump destinations. We will examine each format in detail in the upcoming slides. Okay, this slide shows the R-type format, which is used for register-to-register arithmetic and logical operations. R-type instructions have 6 fields. The opcode is 6 bits and identifies the instruction type. For R-type, the opcode is typically 0. The RS and RT fields are 5 bits each and specify the two source registers. The RD field is 5-bit and specified the destination register where the results will be stored. The shared field is 5 bits and specifies a shift amount for shift instructions. The func field is 6 bits and tells the processor exactly which operations to perform, such as add, subtract, or AND. All arithmetic and logical instructions that operate on registers use this format. Operands must be registers, not memory locations. Here is an example. Add T0, T1, $T2. This instruction adds the values in register $T1 and $T2 and stores the result in $T0. The RS field would contain the number for $RT1, RT for $T2, and RD for $T0. The opcode would be 0 and the func field would contain the code for the add operation. This consistent format makes decoding simple and fast, which is a key RISC principle. Okay, this slide covers the I-type format used for instructions that include an immediate value. I-type instructions have 4 fields. The opcode is 6 bits and identifies the specific operations. The RS field is 5 bits and specifies a source register. The RT field is 5 bits and typically specifies a destination register for a second source. The immediate field is 16-bit and contains a constant value. This format is used for 3 main types of instructions. First, data transfer instructions like load and store. For example, LW $T0, 100 $T1. It loads a word from memory. The address is located by adding the immediate value 100 to the contents of register $T1. The loaded value is stored in $T0. Second, immediate arithmetic operations. For example, add $T0, $T1, 5. Adds the immediate value 5 to the contents of register $T1 and stores the results in $T0. So the third, branch instructions, which we will cover later. The immediate field in branches specifies how far to jump. This slide shows the J-type format used for jump instructions. J-type instructions have only 2 fields. The opcode is 6 bits and identifies the jump operation. The target address field is 26 bits and specifies where to jump. Here is an example. J-target. This instruction jumps to the address labeled target. The processor takes the 26-bit address from the instruction, combines it with the upper bits of the current program counter and continue execution from that new address. Jump instructions are used for unconditional branches, such as going to a function for looping back to the start of a loop. The 26-bit target allows jumps anywhere within a 256 megabyte range. Unlike R-type and I-type, J-type does not use any registers. It operates directly on the program counter to change the flow of execution. So that concludes this part of the lecture. We will cover the remaining topics in the next session. Thank you. Assalamu alaikum wa rahmatullahi wa barakatuh.